My fellow Americans, only geothermal energy has the potential to diminish the potential for potential global warming. This is the potential of the potentiality. It could cause what we could consider global winter. What would you do if it was winter all the time? Just what could you do?
Bordering the Arctic Circle, Iceland is home to some of the largest glaciers in Europe. But under the cold surface, the Earth is bursting with heat. Iceland is one of the most geothermally active places on our planet. Experts explore the area using a variety of methods to understand this form of energy. Gylfi Pálsdóttir is a geophysicist from Iceland Geosurvey. He has studied geothermal fields all over the world.
Geophysics is meant to X-ray the Earth, to see what is going on at tens of kilometers depth.
Anna Wairimu is part of the geophysics team from Kenya's power utility, KenGen.
Yeah, so we go in this direction, to the direction of the smoke.
She is in Iceland to perfect her exploration skills by studying with seasoned experts like Gylfi in the geothermal training program of the United Nations University.
When you're studying geology, to me, it's like you're in an adventure and you want to unravel what was happening in the past. The history of how the earth was formed. It's great to know all of that. It's like you're going back in time, and it's what is fascinating.
Iceland's geology is truly unique. It sits on the border of two of the large tectonic plates that form the Earth's surface. These two plates shift apart by 2 centimeters per year. Over the millennia, this movement has created the geologically significant rift valley known as Þingvellir. The separation of the plates allows lava to move closer to the Earth's surface, creating numerous volcanoes and geothermal fields, which heat up underground water and steam. The job of geophysicists like Gylfi and Anna is to identify and discover as much as possible about the geothermal fields and figure out the best places to drill holes to extract this energy. Iceland is harnessing its wealth of geothermal resources. Drill holes up to 3 kilometers deep tap into high-temperature water and steam that shoots up towards the Earth's surface with high pressure. A system of pipes takes the mixture of water and steam to one of Iceland's 5 major geothermal power plants. The steam and water are separated, with steam used for electricity generation. An international group of geothermal practitioners is visiting one of the plants as part of the UN University Geothermal Training Program.
And then the steam is taken here to this small units here. These are also the separators, separating the last remaining droplets from the steam. After that, the steam is dry and can be used directly into the turbines.
Iceland's geothermal plants generate between 60 and 303 megawatts of electricity each. Anna is part of this selected group of engineers and scientists from more than 50 developing countries. They have all come to learn from Iceland's experience in utilizing its geothermal energy. Around 26% of Iceland's electricity comes from geothermal energy. The plants also heat fresh water, which is transported to towns and cities in pipes, such as this one that runs for 27 kilometers from Nesjavellir power plant to the capital, Reykjavik. The hot water is first stored in big tanks and then distributed throughout the city, where it is used in a variety of ways. Additional hot water is obtained from lower temperature drill holes under the city. Water, heated at 73 degrees Celsius, flows from the taps of houses in the city. Additional home hot water systems are then not needed. People are charged according to the amount of hot water they use. Hot water is also used to heat 90% of the houses in Iceland, not only in the harsh winters, but also in summer, which can still be chilly. Anna and the fellow classmates she shares the house with use electricity for cooking, lighting and powering appliances. However, the major users of Iceland's electricity are heavy industries, especially aluminium, which is produced in large-scale smelters like this one near the capital. Yet, in the town of Hveragerði, people are finding innovative and diverse ways to use geothermal energy. The town is full of greenhouses, most of them used to grow flowers. And to deal with cloudy days and long winter nights, they are also experimenting with the use of LED lights. Several of the local small industries rely on the direct use of geothermal energy. And now, the town even has a geothermal restaurant.
This is earth cooking, geothermal cooking. This is 170 Celsius hot power and with 14 kilobars, so it's very easy to cook. And here we are doing baking potatoes. Usually in the oven you use a lot of heat and long time. Here only 20 minutes. More or less you can do all you want to do. You have to think how to do it and then you can do it, because this power is very nice and very cheap. Come from here, it's very easy. Like an Arab with oil.
Icelanders love hot pools, which are popular places of leisure. Most of the pools use geothermal water, and some, like the Blue Lagoon, use geothermal water directly from a nearby power plant, which is enriched with silica and believed to have health benefits. Compared to a number of other power sources, geothermal energy has minimal impact on the environment. Nonetheless, it does generate emissions.
In the steam, you not only have water, but you also have a gas. You have hydrogen sulfide, you have CO2 and hydrogen.
Although there are ways to capture the hydrogen sulfide from the plant's emissions, these are costly.
In the power plant, they will separate the gas from the water, and then they release the gas into the atmosphere. And this is becoming a real problem, because the hydrogen sulfide is really corrosive and probably unhealthy, at least in higher doses.
Anthor Iverson works in a research station at one of Iceland's geothermal plants. He is developing an innovative biological solution to reduce emissions, where a special type of bacteria eats the hydrogen sulfide.
They have decided that any future geothermal power plants, at least near cities and towns, will have close to zero emission of hydrogen sulfide.
Geothermal water used by households is also recycled. This water is collected in a pipe system and circulated throughout the city, where it is used to melt snow on roads and sidewalks, making it easier for Anna and her housemates to commute to the UN University Geothermal Training Program, a place for exchange of ideas and knowledge. Professionals attending the training centers around the world with great geothermal potential, like Costa Rica, El Salvador, Indonesia, Kenya and the Philippines. They are here to improve their skills and further develop the use of geothermal energy in their home countries.
It's very important to expand the use of renewables. And capacity building in renewables energy technology is very necessary, and especially in the developing countries, because that is where most of the increment in energy use will be. And it is a great blessing if we have the opportunity to assist countries, tens of millions of people, to harness the resources they have in the ground.
Over 20 countries worldwide are generating electricity with geothermal energy, and more than 70 are using geothermal water to heat houses, for bathing and in industry.
I think geothermal is the future. It is a resource that is renewable, and it's a clean energy. We don't have to pollute. It is one of the ways of securing our energy for the future.
So remember that you have your lectures available to you here. Topic 5 in this lecture 3 that we're looking at right now, Icelandic geothermal. You can look at this, and if you need some more information you can come back to this. But let's take a look now at the Trans Energy Project, see what's happening. The Trans-Boundary Geothermal Energy Resources.
The Central Europe program supports cooperation among the countries and regions of the area to improve innovation, accessibility, responsible use of the environment, and to enhance competitiveness. The program is financed by the European Regional Development Fund and runs from 2007 to 2013. It invests 231 million euros to provide funding for successful projects. The sustainable use of natural resources based on geoscientific expertise, including energy resources needed for everyday life, goes beyond the interest of the targeted countries. At present, 20% of the Earth's population consumes the majority of the energy produced. If all 7 billion people of our planet use the amount of energy consumed by an average European citizen, the present energy resources of the Earth should need to be doubled. By 2040, when the Earth's population is estimated to reach 9 billion, another 2 planets will be required to supply sufficient energy sources. In our increasingly contaminated world, humans are just in time to start looking for renewable energy resources that do not impact on the environment. In the Pannonian Basin, geothermal energy has the highest potentials as a renewable energy source. Partners in the TransEnergy project, led by the Geological Institute of Hungary, are the National Geological Surveys of Slovakia, Austria and Slovenia. The aim is to promote the sustainable use of geothermal energy in the western part of the Pannonian Basin, based on the results of clear geoscientific investigations. The use of renewable energy resources is not only an environmentally responsible aim, but also has economic and social benefits. In addition to being environmental friendly, it reduces the energy import dependency and thus increases the security of supply. The energy import of Central Europe is significant, which increases the vulnerability of the region. Among the countries participating in the TransEnergy project energy, the import rate is the highest in Austria, but also exceeds 50% in the other countries. Furthermore, the use of renewables helps to reduce the carbon dioxide concentration in the atmosphere derived from the burning of fossil fuels, one of the factors most cited for being responsible for climate change. Setting. Going downwards in the subsurface, the temperature increases by 1 degree Celsius per 33 meters. This is the geothermal gradient.
Good stuff, right? Geothermal gradient. So make sure that you get the meat there.
Going downwards in the subsurface, the temperature increases by 1 degree Celsius per 33 meters.
Every 33 meters, 1 degree Celsius in general.
This is the geothermal gradient. In the Pannonian Basin, this value is 18 meters. In other words, the temperature increases faster and the value of the geothermal gradient is about 1.5 times greater than the global average. These favorable geothermal conditions are related to the formation of the Pannonian Basin about 10-12 million years ago, when due to stretching, the lithosphere thinned and the hot asthenosphere got closer to the surface. 1,000 meters below the surface, the temperature is about 60 to 70 degrees Celsius at many locations, and the depth of 2,000 meters, the temperature of the rocks and the fluids stored in their pores and fissures may exceed 120 to 130 degrees Celsius. These hot waters and vapors may be already suitable for the generation of electric power. Thermal groundwaters flow along regional paths on a scale of 100 km, governed by the temperature and pressure differences in the subsurface. These flows are driven by the cold meteoric waters infiltrating in the mountainous areas surrounding the basin. As water percolates, it gets heated and expands. Its density decreases, therefore upwards along favorable geological structures such as fault plains. These hot waters can be brought to the surface from the depths by drilled wells and utilized in many different ways. Geothermal energy is a renewable form of energy. However, it can be utilized only with certain restrictions, namely that the amount of thermal water abstracted does not allow the pressure and yield of the reservoir to decrease. Therefore, the utilization of a hydrogeothermal systems becomes a water management issue at the same time. Experience shows that the possible negative effects of one country's overexploitation, such as decrease in the yield and temperature, are often felt in the neighboring country due to the regional nature of thermal groundwater flow paths. Therefore, only a harmonized transboundary water and energy management strategy can lead to a sustainable utilization of geothermal resources. Vapors from high enthalpy geothermal systems with a fluid temperature of 150 to 200 degrees Celsius can drive turbines and therefore are suitable for direct generation of electricity. However, these systems are mostly linked to active volcanic regions. Medium enthalpy systems with water temperature of 80 to 120 degrees Celsius are mostly utilized in district heating.
So note your term district heating. That would be for your radiators not to generate electrical power, although you'll see that we'll have binary systems that allow these lower temperatures to be used to generate electricity. But the district systems are like you saw in Iceland, where they heat their homes, swimming pools, hot water for their domestic.
The commonest are low enthalpy systems with water temperature of 70 to 80 degrees Celsius.
Low enthalpy systems. Here's what I consider to be the main emphasis of our course, is the use of ground loops or earth coupling techniques. In other words, this is an air, this is a fluid loop here, and they're indicating air here. So you can see that this is similar to the layout that we were looking for in our theoretical ground loop that we were going to determine the usefulness and some numbers for the Blackfeet Community College. This is an air system where you would circulate air in a continuous loop this way. I'm not quite sure what they're trying to show here, because I mean this has to come back to the house.
And below, which have a wide range of utilization possibilities.
There it is.
Individual space heating, heating of greenhouses, industrial processes, fish farming, snow melting. The most widespread utilization of low enthalpy systems is balneology, as thermal waters often have a high dissolved
Key, low enthalpy. Key term.
Content. They can be used for medical purposes as well. The Carpathian Basin is famous for its spa tourism. In the case of balneological utilization, the heat content of the thermal water is often not used for direct heating purposes. In fact, if the water temperature is too high, it is often mixed with cold water before it is let into the pools. The TransEnergy project focuses on 5 transboundary pilot areas of Hungary, Slovakia, Austria and Slovenia, where unharmonized thermal water utilization has already led to conflicts. A user-friendly web portal will make all relevant information about the utilization of geothermal energy in the region available to stakeholders and the wider public. It will be known where and how much are the reserves, which quality and quantity changes are foreseen in the thermal groundwater flow systems due to water abstraction, what experience has been gained from the existing production, and where and for which purposes geothermal energy can be used. The cross-border area between Slovenia, Austria and Hungary has a very good geothermal potential. This is the only area in the entire project region where a small Austrian power plant produces electric power from geothermal energy. Abstracted thermal water is also widely used for district heating, for example in Lendava and Murska Sobota, as well as for the heating of greenhouses. Furthermore, balneological utilization.
Whoa. Wait a second. Looks like we had a little issue there with an update, automatic updates. Here, let's get you back into that and finish up that. Not sure exactly where this thing cut in, so let's start it right here.
The cross-border area between Slovenia, Austria and Hungary has a very good geothermal potential. This is the only area in the entire project region where a small Austrian power plant produces electric power from geothermal energy. Abstracted thermal water is also widely used for district heating, for example in Lendava and Murska Sobota, as well as for the heating of greenhouses. Furthermore, balneological utilization is also widespread. In the Hungarian-Austrian cross-border region, conflicts of thermal water utilization, started with the construction of a spa in Lutzmannsburg. Due to the water abstraction in Austria, a continuous drop in the groundwater level was observed in Hungary. A similar situation is found in the Danube basin, where geothermal energy is utilized both by Slovakia and Hungary by the abstraction of thermal water from a reservoir at a depth between 800 and 2,500 meters. Decrease in the discharge affect both countries.
See, the issue here can be solved by re-injection, by using and then re-injecting the water, and we'll see more about that when we get into enhanced geothermal systems, or EGS, in the next few weeks.
In the Vienna Basin, potential conflicts with hydrocarbon exploration, which targets the same reservoirs, is at the center of our investigations. Despite the fact that the central part of the basin is as deep as 6,000 to 7,000 meters, where water temperature can exceed 200 degrees Celsius, geothermal utilization has not yet been established. Water withdrawal due to mining activities in the 1990s seriously affected the groundwater resources of the fifth pilot area in Hungary. Depressions caused by these abstractions resulted in the drying up of natural lukewarm springs and the decrease of discharge and temperature. Since mining-related water exploitation has stopped, the rehabilitation of the groundwater system has started. By the 2013, when TransEnergy finishes, the sustainable utilization of geothermal resources is expected to increase, and other regions will also benefit from TransEnergy experiences.
There you have it, up to 2013. So that rehabilitation